Hi folks, welcome to this lesson on what I'm calling sneaky trig identity stuff. There's not really any new information in this one, so I'd really recommend that you give each of these questions a shot before you watch me do them, or maybe if you need a little help getting started with the first little part and then you sort of find what the technique is, then you pause and try and polish it off. So here we go, sneaky trig identity stuff. 14 sine x cos x can be written in the form a sine bx. So let's do it. So something weird here. We have sine x cos x. It's probably making us think about this kind of identity, the fact that sine 2 theta is equal to 2 sine theta cos theta. And we're doing all this stuff with our formula book in hand. So the question is, can I rewrite this as 2 sine x cos x? Well, not really, because there's a 14 in front. But I could write it as 7 times sine 2x, or 2 sine x cos x. And the identity is that if I have this, okay, just like this, then it is equivalent to this. So what do I really have? I still have that 7 out front, and it's 7 sine 2x. And that's written in a form that is probably computationally more elegant. It's easier for us to understand what the graph itself looks like. And this idea that many complicated shapes can be represented by basic sine graphs or building blocks of sine graphs is actually a really deep idea that leads us to stuff like the fast Fourier transform that can use for hunting down electrical noise, or basically for all digital analog conversion of sound. All right, here we go for another one. Tan theta is 3 over 7. So we do have this kind of identity, but it doesn't involve tangent. We have this kind of identity. Okay, tan theta is sine theta over cos theta, which you might be able to use. I mean, in this case, that's 3 over 7. Though sine can't be 3. It must be 3 over something. I think what you should do in this case is think about just basic old grade 10 trigonometry, right-angled trigonometry, and we'll deal with the quadrant later. So if this is the angle, tangent is opposite over adjacent. Okay, so it would be 3 over 7. And I could figure out this hypotenuse, which I'm going to need to find sine, by using straight-up Pythagorean theorem. So c squared is a squared plus b squared, so c squared is going to be 7 squared plus 3 squared, or 49 plus 9, or c squared is 58, or c is root 58. And we can just leave that in exact terms, especially if it's paper 1. There's the triangle that we're talking about. So on that triangle, sine is the opposite over the hypotenuse. So sine theta is going to be 3 over root 58. The only thing we have to worry about here is what quadrant we're in. We are in quadrant 3. So in that quadrant, it's going to be negative. Now, if you really wanted to, you could have drawn this in the quadrant, and you would have had something like this, so negative 7 and negative 3, and it would have let you know that the y values are negative. I think it's really more hassle than it's worth, though. Just find the value and then account for the quadrant you're in by changing whether it's positive or negative. So there's our result, and here's our result for the first one. Last one. I'm including this because it's one that came up in an exam a few years ago, or something similar came up, and it was a pretty sneaky one, I thought. And I had a lot of students ask me, but which theta are we talking about? So the triangle below has an area of 10. It's known that sine theta is 2/5, and we're supposed to find x. And the classic trig thing would be to circle it and say, there it is. But that's going to get you 0 marks, so let's not. What I think you should notice here is that this full angle here would be sine 2 theta. Okay? And in this big triangle, the area of the big triangle, area of big, is going to be 1/2 one side times the other side times the sine of the angle between them, which would be 2 theta. Okay? That's kind of what we're going to work towards. And that comes from your formula booklet. The area of any triangle is half AB times the sine of the included angle. That's stuff that maybe will help us get started, but I gotta find sine of 2 theta. And so that makes me think, okay, so sine 2 theta, what do I know about that? Again, just pause at any point if you feel like you've got some insight and try this. Watching me do it is going to be a million times less useful than even taking a bunch of wrong turns yourself. I know that sine 2 theta is 2 sine theta cos theta. Okay, so I do know sine theta. I don't know cos theta. So now I've got to take another turn. Sine 2 theta was the thing I wanted. Now to find that, I need to know cos theta. So that's going to send me to this idea. The Pythagorean identity is the way that we can connect sine and cosine. So for us, it will be 2/5 squared plus cos squared theta equals 1. And by definition, those thetas have to be acute. If they were both bigger than 90, then the total angle in the triangle would be over 180, so it wouldn't be a triangle at all. All right, let's work this through. And I feel like we may need a bunch of space. So I have cos theta equals, I'll write this as 25 over 25. We've done a bunch with that denominator, but that's just a coincidence. Okay, we'll have 21 over 25. I got to square root it, so that would give me plus or minus the square root of 21 over 5. But theta is acute, so cosine's positive. Oh my gosh, that's a lot of work just to figure out what cosine is. But hopefully from there, things will start to crumble. Once I know this, I can find sine 2 theta, which was part of the big triangle. And again, the reason this is sine of 2 theta is because it's 1 theta plus another theta. And they both have the same value. They both have the same variable, so they have the same value as a number when we figure this out. So sine 2 theta is going to be, let's see, 2 sine theta cos theta. And we found that out to be 2 times 2/5 times root 21 over 5, or 4 root 21 over 25. That is the sine of this big angle over here. Great. I'm going to have a hard time fitting this all in, but I'll do my best. I'm going to come back to it on the left here, where I had already set up the question. And now I can put more stuff in. I do know that the area is 10. It's going to be a half times x times 15 root 21 all over 4 root 21 over 25, because that's what sine of 2 theta is. We just found it up here. I'm going to need to do some reducing fractions. Otherwise, these numbers are going to be real big. So 15 over 25 is 3/5. 4 over 2 is just 2, so that's gone. So what am I going to get? I'm going to get 10 equals 6 root 21 times root 21. Okay, that's just 21. So 6 times 21 all over 5x. And now this is a little bit unpleasant. I think what I'll do is I times both sides by 5, so I'll get 50 equals 6 times 21. So I could, if I'm stuck, just go to my traditional algorithm. Oh, that'll be 126 equals 126x. And now it's really crumbling, hey? Now we can just go and divide by 126, and we'll get an answer. X is going to be 50 over 126, exactly. You can reduce that down if you want. You can call it x equals 25 over 63. These are not two different answers. They're the same answer presented differently. But the IB doesn't care about you reducing your fractions unless it's going to turn into an integer value. So you can just leave it as 50 over 126. Okay. Same thing. There's no practice around this, but it may help you do some of the stuff that was assigned before. I hope you found this helpful. I hope that's a good sort of intro to a trickier problem, and one where you really have to go to your formula booklet and see what are all the things that are at my disposal. Good luck with the material, folks, and take care.